We saw in the previous video what happens when two traveling waves coincide in the same space with each other by exploring the principle of superposition and how that applies in the case of constructive and destructive interference. In this video, we will describe what happens when a wave reaches a boundary. But before we do that, let's answer the following question. What do you think is going to happen to this one-dimensional traveling wave pulse when it reaches the boundary? We can see from this animation that the wave will be reflected, but how it's reflected depends on how the wave medium is connected to the boundary. When a wave pulse reaches the end of the string, it appears to be fully reflected. Because the support attaching the string is rigid, the pulse does not transmit any part of its disturbance to the fixed point, and its amplitude does not change. Note, however, that the reflected pulse is now inverted. Each point of the medium is now displaced in the negative y direction. This can be explained as follows. When the pulse reaches the fixed point, the internal storing force in the string produces an upward force on the support point. In accordance with Newton's third law, the support must then exert an equal and opposite reaction force on the string that is directed downwards. This downward force produces the reflection pulse that is inverted upon reflection. Let's now consider the case where the boundary point is allowed to move freely in the y direction. The tension at the free end is maintained by tying the string to the ring of negligible mass that is free to slide vertically along the post. It can be seen that when the pulse reaches the end, it appears to be fully reflected. Note, however, that this time the reflected pulse is not inverted. As the pulse reaches the ring, it exerts a force on the ring, causing it to accelerate in an upward y direction. In the process, the ring would overshoot to twice the amplitude of the pulse. The ring reacts by creating an opposing force which brings it down. In the process, it produces a reflected pulse that is not inverted, but with the amplitude that is the same as that of the incoming pulse. So when a traveling pulse reaches a boundary, it will be reflected and inverted if the boundary is a fixed point, and it will only be reflected if the boundary is free to move. Assuming that no energy was lost in the process, then the reflected pulse will have the same amplitude as the incoming pulse for both the fixed and the free ends. So what about the velocity of the reflected pulse? Assuming that no energy was lost in the process, the reflected pulse will move with the same speed but will move in the opposite direction of motion. So although the magnitude of the velocity remains unchanged, the direction of the velocity has clearly changed, and therefore the velocity of the reflected pulse is different. Finally, we may have a situation in which the boundary is neither fixed nor loose. In this case, where the boundary is an intermediate between these two extremes, part of the traveling pulse will be reflected and part will be transmitted. For instance, suppose a light string is attached to a heavier string as shown in the simulation here. When a pulse traveling on the light string reaches the boundary between the two, it can be seen that part of the pulse is reflected and inverted and part is transmitted to the heavier string. As expected, the reflected pulse has now reduced in amplitude simply because part of the energy that was carried by the original pulse has now been transferred to the transmitted pulse moving on the heavier string. The reflected pulse in this case is inverted for the same reason described when we explored the case of a fixed end. On the other hand, if the traveling pulse moves from a heavier to a lighter string, then part of the pulse will be reflected without being inverted and part will be transmitted to the lighter string. In either case, the amplitude of the reflected and transmitted pulses will depend on the relative densities or the mass per unit length properties of the two strings. When a pulse is transmitted from one medium to another, does its velocity change? We saw in a previous video that the wave velocity is inversely proportional to its mass per unit length. The heavier string has a greater mass per unit length, and therefore the pulse will move at a slower speed on a heavy string than it would on a lighter string, assuming that they are both under the same tension. So a pulse transmitted from a light string to a heavy string will slow down, and the pulse transmitted from a heavy string to a light string will speed up. The speed of the reflected pulse remains the same, but it just changes directions. In summary, a traveling wave will be reflected when approaching a boundary. Total reflection and inversion of a traveling wave takes place when it reaches a fixed boundary point. Total reflection but not inversion of a traveling wave takes place when it reaches a boundary point that is free to move. Partial reflection and partial transmission will occur when there is a change in the medium transporting the wave.